Hi folks, welcome to this first video in a series of videos on coding and control. In this particular video we will be implementing a PI controller or proportional integral controller from scratch, and I will assume that you have no programming experience, so we'll go over the basics there. We'll be using Python in particular to implement this controller, and I will have timestamps both as chapters in this video and in the video description, so you can skip ahead if you're already familiar with Python or some basic coding in general. So, what's the outline of this tutorial? We will implement a PI controller in Python, and I'm assuming no knowledge of programming. So we'll start with some basic programming notions, especially as they relate to what we will be trying to do. Now, let's first take a look at what we're trying to implement, our controller architecture. We can build up a PID controller from different components, and this is the way we'll be looking at that particular controller. So we'll start out from a proportional controller that you can see up top here. So we have R, which is our reference signal, which is what we're trying to track. And then we have a control input U that we can pass into a plant or system that will output its state Y. And we'll try to get Y to track R as closely as possible. So we can start out by using this proportional controller over here, which has this gain Kp, and it just gets multiplied by the error, and that produces our control input. And then we can ramp it up a little bit by adding in some integral action over here, as governed by this gain Ki. And we just sum the two elements, so we get an element P and an element I, and we sum those together to get our control input U. And then finally, which I won't be covering in this video, but you'll be able to implement yourself if you grasp some of the basic concepts presented here, you'll be able to implement a PID controller. So you'll be able to add that derivative action over here, and you'll have that term D that you just sum together with P and I, and you'll end up with a new control input U. So in this particular video, I won't be going into the concept or the principles of PID controllers, or PI controllers for that matter. So if you want to learn more about that, there's a companion article for further reading right here on the Lodestar website over here. And this is a pretty comprehensive overview of the different elements to a PID controller and some additional background information that might be useful to further your understanding, as well as some design considerations. So you'll be able to look through that as you wish to learn more, and to look at some more implementational details and the way we can go about discretizing a controller of this nature. But that's not the focus of this presentation or this tutorial in general. So we'll start out with some basic Python first. So I'm assuming that you have some mathematical knowledge, obviously. So most of these things will relate to how we would do things on paper, essentially, and that's how I'll be trying to get this to relate to what you already know. So we'll start out with variable assignment. So you'll be able to access these slides on the website above, and I will also post some links in the description. And you'll be able to run this code interactively in your browser, actually. So I can essentially just change values, and they will propagate accordingly. So that's quite nice here. You'll be able to do that in your browser without having a working installation of Python. Now, for the purposes of making this some sort of code along session, I will be using a different environment here in Jupyter Labs. So you'll be able to write along if you wish. So we'll start out with variable assignment. Obviously, we don't want to keep working with numbers or different quantities or object types without referring to them by their name, since otherwise we'd have a lot of repeating code, and duplication in code is not efficient. As you would know from writing derivations on paper, you'd rather want to give a group of terms a name if you'll be seeing those terms a lot in the rest of your derivations. So that's the same principle here. So it's fairly simple. You just use an equal sign, and you'll be able to assign different quantities or variables to their particular names over here. And a lot goes here, so we can use lowercase letters, and we can assign whatever we want. So we could say, okay, A is 2.3, and we can say B is 2. And we could even go as far as saying that C is not even a number, but a string, let's say. And we do that using quotes. You'll be seeing these sometimes throughout this tutorial, although they're not the main focus. So I'll be able to say hello. So Python is a weakly typed language. What that means is that we don't have to say or declare what A will be accepting. We can just have A accept a float, in this case, a floating point number. So 2.3, for example. Or we could just change it altogether and say, hey, I want A to be a string now. So we could have it be 2.3 as a string. So as a set of characters here. So this all passes in Python. You don't have to pre-declare what you'll be using, unlike strongly typed languages like C, C++, you name it. So I'll be able to run this, and then we can use our trusty print statement here. So we'll be able to print whatever we've seen, and this will work in any sort of implementation of Python. So A is 2.3, but let's say we change this to 2.4, we'll see that A is 2.4. Since we first say it's 2.3, but then we change it to a string here, 2.4. Now we can print B as well, that's 2. And all of this works nicely. So this is the basic principle of variable assignment. You'll be able to do things like this, or you could essentially also do things like saying, hey, I want A to be equal to B now. And that works as well. So B was 2, and A is also 2 now. So you can assign variables to variables as well. So all of that passes. Now that's the basic principle of variable assignment. And I also wanted to touch upon types briefly. So Python, as I mentioned, is a weakly typed language. That means that we'll be able to just pass any sort of type into any sort of variable, and that will work. So A is not bound to be a floating point number, but it could also be a string like I showed here. Now, the interesting thing here is that we can study what the types are that we are dealing with here. These are really basic. So now A is 2.3 again, and we'll be able to use this type function here, and we'll be able to print the type of A, and A is a float, so a floating point number. Now B, on the other hand, is an integer, so that's an int, and C is a string, so it's a string of characters, so that's a string right there. So those are your types, and usually it's useful to know what types you're dealing with when you start running the risk of mixing types that aren't meant to be mixed. So it's good to every once in a while use this type function here to check what types your arguments are, since you can solve a lot of issues that way in general. So that's as far as types go in Python. Now I wanted to look at lists. Lists are extremely useful in Python, especially once you get a hang of them. They just become a really trusty way of packing a lot of data together. So here's a little example. We'll start out by declaring a list. So I'll just use A again as a name here. And we'll just put some numbers in here. So let's say 1, 2, and 3. And the cool thing is that we can just print this and it will return a list, obviously. Now let's say I was interested in accessing one of these elements in this list. I'd be able to do that by using these square brackets. And now here's the thing that differs from other programming languages. So a language like MATLAB starts from 1 with their indices. In Python you start from 0, like in C or C++. So if I want to access the first element of this list, so there's 3 elements, the first one would be indexed by 0. So this is going to print 1. Now I'll be able to access the second element, and that is going to be 2, and I index that by 1. So that's 0 plus 1. And then the final element is element 2, and that is evaluated as 3, as we expected. Now, let's take a look at what we can do with lists. So let's say I initialize an empty list here. We can take a look at the length of these lists. So let's say I do want to access an intermediary variable, but I'm also interested in the length of the list. Maybe that's useful to access the same element in another list, or to combine 2 lists, you name it. Then there's this function here that's called len for length. You'll be able to just pass in, let's say a, which we expect to give 3, and lo and behold, it gives us 3. Now b is an empty list, so we'll be able to, see that this is 0, and there you go, it's 0. Now let's say I have a list C, and now I want to do something a little different. I want to combine different types. So let's say we have 1, 2.3, and we have hello. Will that work, or won't that work? We'll see. Well, no errors. Let's take a look at the length first. Seems to be 3. Things seem to be looking up. And then we can just start accessing the different elements again. Hey, we see 1, we see 2.3, and we see hello. So as I mentioned before, Python is weakly typed, which also means that you can combine different types in the same list. This is not the case in other strongly typed languages, where you have to use particular types all throughout the same list. Not the case in Python. So that can afford some nice mixing that can be useful, but it can also be a liability if you don't keep track of your types. And that's all your own responsibility. So it's just a word of caution here. We'll be able to check that these are indeed still the types that we expect them to be. So this should be a string. There you go, it's a string. This should be an integer. And the second, 2.3, should be a float. So all good to go there. You'll be able to play around with these same constructs in your browser in these slides. So we'll just skip over this for now. And then we can look at some arithmetic. In this particular tutorial, we only consider arithmetic on integral types. So you'll be able to do a lot more things once you start getting familiar with how different types behave with these operators, but we'll be just looking at these for now. So let's define some things again. So let's just stick with the same definitions as here. So we said a equals minus 1.4, b equals 2.3. Now let's see. We can negate a, and if we do so, we'd expect a to be evaluated, so minus a basically to be 1.4. We can check that. There you go. And this is called a unary operator, so it takes a single operand, a. And now we go to the binary operators, so we can add a and b. And doing that will give us 0.9. And here you see some of the effects of floating point numbers. It's not quite 0.9 because of the way the computer stores floating point numbers. There's obviously ways around that, but this is useful to keep in mind. You're working with a computer, there's finite precision, and this is something you'll have to live with. So it's fun that we saw this popping up right here. Here in this particular evaluation, we don't see any of that, so that's quite interesting. Now we can also subtract a minus b, and that will give us minus 3.7. Again, these floating point rounding errors. And we'll be able to multiply them. So that's A times B with an asterisk. So, obviously that's minus 3.22. And we'll be able to divide A by B. And, that also checks out. This is a little longer, obviously. But here you go. That's your decimal expansion right there. So these are basic operations. Then we can also do powers. Now, I won't be using POW here. This is a reserved argument. You can see its color changed here. We'll just use PW here. I'll be able to do that using a double asterisk here, which you might be familiar with this particular notation, but that does not work here. This is a different bit operator here. So we'll just, let's say, cube it. So A cubed will give us minus 2.744. Again, with those floating point errors. So those are your simple operations. You'll be able to play around with this and make your expressions more complicated. Let's say you can add them on the same line. Obviously, there's no real restrictions there. Just be careful when you concatenate these operations that you're better off using parentheses for readability and peace of mind, since it's not always clear what is going on. So, if I were to do something like 2 plus 3 divided by, let's say 1 plus 4, then this is, unlike what you'd expect in particular circles, you'd actually have to parenthesize this particular term and these two terms. Otherwise, your function will evaluate to 2 plus 3 over 1 plus 4, which is not equal to 1. So obviously that's 9 right there. 5 plus 4. So that's where parentheses will be indispensable, pretty much. So that's this basic manipulation of variables. And we can look at some more variable assignment. We can actually, immediately combine these operators here, the binary type at least, with assignments. So we'll actually be able to say, hey, I want to take A and I want to add to it 1. So that's A plus equals 1. And this is just equivalent to saying A equals A plus 1. So it's just shorthand. And this is extremely useful, especially if you want to increment, let's say, a time variable by delta t. You'll just be able to do that all the time. Same holds for minus equals 1, and so on and so forth. So you'll be able to multiply and divide. There's no such thing for taking a power, but you'll have plenty to work with here already. So here's a little example there. You'll be able to play around with that. Then I want to look at some booleans. So booleans are basically binary constructs. So there's only two. There's true and there's false. Now, these can be quite useful since statements in general, are deterministic in Python at least. If you define them properly, you'll be able to have one outcome that is true and one outcome that is false for one particular set of comparisons, let's say. So booleans are useful since we can say A is equal to true and B is equal to false, and then we can try to reason about how these things will work for us in practice, since oftentimes we'll want to change the behavior of a program depending on whether or not a condition is satisfied, and this is the mechanism to do that. So knowing how to manipulate your Boolean variables is extremely useful. So we can take a look at some stuff. We could say A and B. Now what this expects is that A and B are true, They are not, so this must return false. So let's use that print statement again for you. So this is false. Now let's say A or B. So if either A or B is true, then this returns true. And that is true. A was true. Now let's say I wanted to negate one of these. It can be useful in some cases. So let's say it's pretty easy. You can do not B, which should be true, and it is true, because not false is true. And we can, do A and not B, let's say. So that should be true, since it says A and not, so true and not false, which is true, and true, which is true. So there you go. Now you can combine these. Python is a little different from other languages in that you really need to use these in this capacity. So these sort of English terms. In other languages, you can use symbols. Now there's one case where we can use symbols or words, essentially. It's by using this is. So A is B, it should be false because true is not false. And we'll be able to evaluate that as false. A is not B, that is true. So we can also say this, the double equals, checks if they're equal, and that is false. The exclamation point equals checks if A is not equal to B, and that is true, as we saw in Word there just a second ago. So this is your basic, comparisons, basically. Or at least, with these equals and not equals and or and not. One final thing, I just introduced this exclamation point all of a sudden. This is actually equal to saying not, like I mentioned before. So I can say A equals not B. And I'll actually have to parenthesize that here. So there's just a little quirk there. So that was true. Or I could say equals exclamation point B, and that will also not work. So, well, you're better off actually just using this in general. In other languages, that would have worked. Not here. So there's some caveats there. So yeah, those are your booleans. Now, as far as comparisons go, these can be quite useful, and we'll just start with comparing numbers, since we're familiar with how that works. So we can check if A is greater than B, which it is not, so that should be false. Is it smaller? That is true. So this is just your greater than, equal, or greater than, less than signs. And we can actually say less or equal by just taking that, greater or less than sign and then adding an equals sign. And this was true, and this is false. So those are your comparisons, essentially. And then we also obviously have our double equals here for equality, and our exclamation point equals for inequality. So you can play around with these, obviously, and each one of them has a counterpart there. So those are your comparisons. Now, this is all nice and fun. We've found out what booleans are and how they could be useful. They tell us if something is true or false. And we've looked at some basic operations here that are useful in almost any program if we're trying to manipulate things like that. Now, here we introduce something that's known as control flow. Control flow is basically things like checks, basically. So checkpoints where you branch out into different types of behaviors, or you repeat a certain behavior. So we'll start out with the branching type, where we check if something is true. So we'll start again with these values, and we'll actually print. Let's just take A, or let's take A and B. Okay, we'll actually print something depending on how A and B relate to each other. So we'll say if A is less than B, we're going to print A is less than B. And now that's your if statement. There's multiple routes we can go now for the other cases. We can either start a new if statement, or we can be a little smarter and make it part of the same sort of block of control flow, essentially. So you can say elif, which is short for else if. So if the first statement is not true, we'll jump down to the second one, and it also expects a little boolean here. So we'll be able to check if A equals B, and then we'll say, hey, A equals B. And in all other cases, so else, we'll print A is greater than B. So obviously A is less than B. Now let's see if this works in general. Let's make them the same. A equals B. Let's make it bigger. A is greater than B. So we're all set here. Extremely easy to use, but extremely powerful. So you can actually nest them. You can have multiple conditions. You can say, hey, if A is equal to, let's say 2.5, if that has any special significance, we can say something else. A equals 2.5, Maybe that's something special, so you can do that. And, that's how you add some variety in the mix, and this could be useful for your particular case. Let's say if there's different ranges of numbers, you could have these different else if statements that check if it's part of a particular interval that you're interested in, and that evokes a different kind of behavior. So that's where control flow of this nature is extremely interesting and useful. So these are your if statements. There's some more control flow. We'll actually be able to look at this type where we work with lists. So going back to what we saw previously, I'll just copy this code here. Let's say B is empty now, but I want to populate B with elements from A multiplied by -1. Let's say I want to take the negative of A or of each element of A. So the way you do that is you use a for loop. So this is essentially your for all, basically. So for all AI in A, do something. So we're going to fill B. Now the way we work with lists, and you can read more on this, and there might be a future video where I go into some more of this terminology here, is you can append to B, which just adds an element to the end of B. B is empty right now, so we'll just be adding an equal number of things as the AI that we pass through. So there's 3 of those. So we're going to append to B minus AI, so negative AI. And we'll just print. We'll see what B looks like. Yeah, and lo and behold, that is just what we expected. So this is a different form of control flow where we just go through all elements in this. So let's say I had a list of tasks or a list of objects that I wanted to manipulate. I can just loop through them like this. Now, for a particularly simple expression like this, there's one more advanced trick you can use. You don't have to particularly use this, but I find it useful in cases that are still understandable. I can equivalently express this as a 2-liner. So A, I declare A, and then I declare B. And the way I declare B is I go in and I say for AI in A. Now what do I do for that? So I'll take minus AI for every AI in A, and that will constitute B. So let's take a look at what B is now. It's all the same, and this is a lot simpler. So this is useful. Yeah, so these were 2 types of control flow that we've seen: if statements and their related constructs, and a for loop. Now moving on from there, we can look at while loops. While loops are also useful. sometimes even more so than for loop, since we'll just be able to check if a condition is true. So let's say I wanted to, let's do something interesting, right? So I've got a equals 10, and I have a dA basically that I'll try to decrement a by let's say 1. Or maybe let's throw something interesting into the mix, 0.75. Now I can make a while loop. So while a is greater than 0, we're going to be decrementing dA like that, and we'll print a. So we'll print the new a. And this will happen all the time while a is greater than 0. So we expect the final a that it prints to be negative. There you go. The last one is minus 0.5. So that's your for loop, right? Your while loop right there. So it just keeps checking if this condition is true. If it is true, it keeps doing whatever is in here. If it's false, it will just jump out of this little block here. And one thing you'll have to notice here, which I didn't really touch upon, Python is really picky about indentation. So if I decide to use 4 spaces like this, I need to keep using 4 spaces. If I am more inclined to use a tab, then so be it. You need to use that tab everywhere. If I just want to use 2 spaces, even my IDE is already complaining. It's like, hey, this doesn't look like the other things here. So you'll be able to do that, but you'll have to be consistent. So my IDE is expecting, 4 spaces here, so you'll just have to forgive it for that, but it works just as fine. So 2 spaces, 4 spaces, 1 tab, 2 tabs. There's all manner of people advocating for different things. Honestly, you can have your own reasons, but be consistent. If you're working in a group project, set out the rules, set out the way you define things, you name things, you format things, and you'll be good. So different things work for different purposes, and this is one of those instances. So that's your indentation. Python is really picky about that. Other languages use things like curly brackets. You don't have those here, so you'll just have to get used to getting code with a lot of nesting or indentation, depending on the complexity. And if you see that happening too much, there's a couple of tricks that can make your code cleaner and prevent it from turning into spaghetti code, as you wouldn't want your code to be perceived. So we looked at the different forms of control flow here, at least the basic types. Now let's take a look at functions. Okay, so I'll make a little simple function here. So let's say I have a and it's minus 1.4 and b is, let's say, 2.3 again. I'll make a function this time. So you start that out by def, which says that I'll be defining something. What will I be defining? I'll be defining a function that takes the absolute value, just for the purposes of demonstration here. So def absolute, it will take an argument v, and you can name that whatever you want. You can have multiple arguments. There's a lot of things you can do here. So I'll actually be defining 2 functions here, just for the sake of showing that we can have multiple arguments. We'll first start out with an absolute value. So now we'll be using our knowledge of control flow here. If a is greater than 0, we'll return, let's see, we can actually do greater or equal to 0. We'll return a v, and this shouldn't be a, this should be v, so almost gone wrong there. Else return negative v, because that means that v is negative, so we'll have to make it positive. And yeah, we can now just execute that. So in the case of a, we expect 1.4, there we go. In the case of b, we expect 2.3. Now let's make a function with 2 arguments, and we'll be able to say, hey, give me, let's see, let's define a signum So it's gonna tell us, yeah, let's see how we deal with this. So let's call it relative signum. So we'll give it two values, so v1 and v2. If v1 is greater than v2, we'll return 1. If it's equal, we'll return 0. If it's less, we'll return -1. Maybe your particular code uses this sort of logic a lot. Well, make a function. It's a lot easier. So if v1 is greater than v2, we return 1. Else, if v1 equals v2, we'll return 0. Else, we'll return -1. So let's take a look. We'll just reuse this, relative. There you go, a comma b, so that returns -1 as expected because a is less than b. Let's say I swap the two arguments. Obviously the order matters. There's no telling what v1 and v2 are. And that is giving us 1 right there. And b should give us 0. So that's all as expected, and this is useful. This prevents code duplication, makes your code cleaner. If you and anybody else who's working on the same project or code understands what this means, then that's useful. Otherwise, you can document the code, but that's something for a later installment. So there you go, that's your functions, extremely useful. Now, finally, I wanted to talk about some external capabilities here that you can pull into Python. There's also some built-in capabilities that aren't exposed to you because you might not need them. So that's just to prevent unwanted bloat. Now, modules are useful in that they can provide additional, let's say external, maybe internal capabilities to your program. In this particular example, I'll be showing you the time module, which is a built-in Python module. So we'll just be able to say import time. So that means that we'll be importing time, which sounds like a pretty grand thing to do. Now, time affords us with several functions. So we can actually take a look at the documentation here in a second. But I'll tell you one thing. There's this function time in time. So the way you access things that are nested as part of this module name is by just using this dot notation, essentially. And then you call this function with the parentheses, and it takes no arguments. So this gives us a Unix timestamp. So that's the time in seconds since January 1st, 1970. So just to show you that you can't really mess around with functions, I just want to revisit this and say, hey, let's do something that's not allowed. So we set that this takes 2 arguments. Let's give it 1. And it says, hey, it's missing 1 required positional argument, v2. There you go. What if we give it 3 arguments? It says it takes 2 arguments, but 3 were given. So you can't really make mistakes like this. Python will raise errors like that for you. So it's useful to study these errors and try to understand them, as they will often give you useful pointers that will just bring you to the root cause of whatever problems your program is facing. So this time is obviously it updates whenever I call it. It's actually quite useful, and of course there's more accurate ways of obtaining the time, but this is a really nice, quick and dirty way. You can just hand this number to anybody else and they'll be able to convert it to any time zone, any date and time that they would want. So very useful right there. So that's your time module. Here's just a little example. You can actually run this in your browser, so that's pretty neat. One final thing that we'll be using in our example in a second here is time.sleep. And we'll have 1 argument that takes the number of seconds you want to wait. So I'll just show you by way of example here. That's exactly what it does. So it takes the time here, then it waits for 0.5 seconds, and it prints the second time, and then it prints the time difference. Now it's not exactly 0.5 seconds because there's some lag and some delays here, but in your implementation that might be a lot more accurate, and we can actually try to get this stuff to work here. There you go, that's one run, that's another run. You can keep trying this. Sometimes it's more accurate, sometimes it's a little slower. But it's useful for quick prototyping if you don't really care about these timing errors. Otherwise, there's more sophisticated methods, but we won't go into that for the purposes of keeping things nice and concise here. So that's one of the external modules. Just a little tip here. There's internal help in Python. You can just say, hey, give me some help with time.time. And there you go. It returns a floating point number. It returns the current time in seconds since the epoch. And this particular epoch is the Unix time epoch, like I mentioned, January 1st, 1970. Yeah, so fractions of a second may be present if the system clock provides them. My particular system does provide them, as you can see here. So that's quite useful. Otherwise, we wouldn't really be able to capture resolutions like this at all. And then we can take a look at sleep. Sleep, and it takes seconds, delay execution for a given number of seconds. The argument may be a floating point number for sub-second precision. It's exactly what we were leveraging here. And yeah, we're trying to get 500 milliseconds of, idle time. And that's exactly what we did. So very useful. You can also go onto the internet and, look at the Python documentation. That will give you a lot more details, and, we'll showcase some, additional capabilities that you might not have been aware of. And of course, there's external libraries that we might touch upon in a later installment. So with this, we can actually get to coding. So we'll start with a basic PI controller, so proportional integral. Now on the website here, you'll be able to read up on some details and whatnot. And there's a little section here that tells us how we go from this continuous time controller to a discretized approximation. There's a couple of things that we use here. E is our error, K, P, I, and D are our gains. We're only using P and I gains here. So the proportional part is useful. There's no approximation, or it's not useful. It's there. It's basically not special. So the KP gain here just gets multiplied by the error, and that gives you your instantaneous proportional component. So writing a P controller is very easy, but there's drawbacks to that you can read up on in the article. And then the I controller here is based on a forward Euler integration step. So there's some errors associated with that. You'll be able to read about that in the article. Essentially, if there's a delta t between the last time that we checked or updated this I, we'll be able to just take that last I value and then add to it Ki times E at that particular time t, multiply that by the time difference since the last time, and you'll be golden. So now here's a little thing here. If you're writing Python programs in general, it really pays off to use this particular guard here. So let's say I share my code with somebody else and they just want to use my functions. They don't want the code to actually run. Then it's useful to put all your code inside of this guard. Basically, it checks if the program is being run standalone in the sense that you're expecting it to be the only thing that's being run. Essentially, it's not part of some different program as part of a module or something. So it's extremely easy to write this if name, the double underscores here are called dunders, and you'll check if it's main. So essentially, if this is the main thing that's being run, and it is in this particular case, so that's why it's executing. There's cases when it's not. Again, that has to do with using your code as part of a different program, things like that. So that's how we start out. This is really, clean in the sense that you can't really go wrong in this way unless you know what you're doing. This is good practice. So that was our main, well, not really function, but our environment where we insert functions or things that we expect to run. Then we initialize some variables. So we need the last integral value, like I showed you there, that I at t minus delta t. We need our last error, not particularly for this implementation, but you'll need it if you want to use a derivative controller as well. And the last time, so that we may be able to calculate that delta t, and then our two gains, so kp and ki. Just set them to 1 for now. So that's the first step. And then we need some helper functions. We need a function that tells us if the controller is running, so we're expecting a Boolean value there. We need to get the state of the system. We need to get our reference. The state or output essentially doesn't really, the I or PI controller, PID in general, is not really concerned with what it's getting per se, as long as it gets something that relates to the state of the system. So yeah, and then there's our reference here, and the control has to be set on the actual system. Let's say you were running this in real life, you'd have some sort of binding or some sort of interface to your actual hardware, and that might be encoded as part of this function. So you don't want to expose that directly, but you'll have a little helper function that is capable of taking you and implementing it or allocating it on your actual actuators. And again, we need time here to be able to keep track of time. So those are our two segments. And then we need some control logic, which happens down here. We'll first take the last time, we'll initialize that as our current time, the time when we started running the program. Remember, we run from top to bottom here, really simple. Then we check, we do things while the controller is running. If we have some sort of timeout or condition that tells us, hey, we don't need to use the controller anymore, then this function will return false. This controller is running function, and you'll exit your while loop. We'll get the current time, which updates at each cycle. Whenever we enter the top of this while loop, we'll get the current time. We'll get our current state. We'll get our current reference. We'll compute our error, which is the reference minus the state or output. We get our proportional term, which is simply kp times error, and we get our integral term I, which is basically the last integral, plus ki, the gain, times our error, times the delta t, which is basically just t, current time, minus our last time. And then we compute control, and control in this case is simply pi, p plus I. So, and then we set that control, we allocate it on the actual system, and we look at our update here, which updates those previous values, which now become previous values because we'll enter a new run depending on whether or not the system is still running. So we update our last error and we set it to our current error, and our last integral is updated to I. So that's your controller. Now we can actually run this. It's quite cool because this is vanilla Python. You'll be able to run this in your browser. Here's that controller. And I've actually populated these statements here. So we want to track, 2. So we just have a little, step response essentially. We want to go to 2. We start out at 0, and we run the controller for 15 seconds. The controller will be running until those 15 seconds have elapsed, and our state gets updated as follows. So it's just a little linear system. So x dot equals 0.1 times x plus 0.2 times u, and this is a little Euler discretization there to get that to work. Now note that there's some little magic here that I haven't discussed. There's these global statements. They will allow us to not just read a capital X or capital U, R or U, but they'll actually allow us to change them as well. And this is important because functions normally don't have the authority to change things that are outside of their scope. So this is required here. We haven't really discussed scope or concepts like that, but you'll just have to remember this as being something you need to do if you want to impart an effect on the global state of X, essentially. So that's what happens here. This is some internal logic. So imagine that this is all some sort of black box to you, and X gets returned from some sort of sensor or some external sensing system. Our reference in this case is constant. It could have been time dependent. It could have been dependent on the inputs of some external system. Let's say I had my hands at the control here, and I could say, hey, I want my reference to be this and that. Then that could be pulled out in this function. But then again, the nice thing about using functions is that you abstract all of this away. You just expect that getState returns a floating point number, that getReference returns a floating point number, that setControl sets your control, and that your control is a floating point number. These are the only things that you enforce, or you at least expect, and whatever their implementation may be, could be as convoluted as anything, you don't really care. So this is a good way to think about abstracting your code, in the sense that you capture key behavior that's really close to your theory, and then do away with the implementational details for whatever system you're using. And that way you can just have your little library of controllers, pull out any controller, and then wire it up right away with all of those endpoints, defined in a simple way, essentially. So that's enough about these functions here that we coined helper functions. Now here in my web interface here, I can't really use this guard, so you'll just have to uncomment this. One thing about comments in Python, which I've been doing implicitly all this time, you just use a pound or a hashtag sign here, symbol, to comment things out. There's a couple of different ways of doing that, but for single line comments like this, that works just fine. And then we get the logic we talked about. I just added a little print statement here. And and I also added a little time delay after every cycle to make it a little bit more, realistic as part of a sample data system. Now, we have the time on the left-hand side, the state, middle, right-hand side is the error. State is 0 at the beginning. We want to go to 2. On the website, there's some information about these controllers and how P controllers have some drawbacks, and you can see that exactly here. You see this? We are expecting to converge to 2, but it's converging to 2.286 or thereabouts, and this is a steady state error. Even after about 14.9 seconds, we still maintain that steady state error. So that's not something you want, and that's something you solve with adding that integral action. This particular controller, I set ki to equals 0, so you can add more sophisticated behavior to a particular controller and just disable parts of it. Now the problem there is that we're still doing these instructions. So one of the things you can try to do is to make some statements that prevent the controller from even entering this part if ki is 0. So you can just do that by using what you learned about control flow just a second ago. I'll actually run this for you right here. So this is all just straight up from what you saw there. So as you see, it's a little delayed because I'm actually physically waiting 0.25 seconds every time. So this gives you, a little intuition as to the time scales of a process of this nature. And again, the error is similar to what we saw before. So, you know, we can actually plot this. I will not in this particular tutorial because I just want you to see how you can do this quickly and, in a sense, get familiar with just looking at numbers and then afterwards plotting and seeing what it looks like in the fine-tuning phase. This is just about a proof of concept. Just want to do something quick and dirty, and this is the way to go about it. Just print everything, print it in real time. It doesn't matter. Might make things a little slower, but you'll actually be able to look at numbers and say, hey, this is what I'm expecting. If it's not, you'll be able to quickly see, hey, my P gain is too large. I'll need to decrease that. There's a lot of oscillations that you can see in the numbers. So getting this intuition or feel for numbers pays off in the long run, and I'm of the opinion that it's useful to get that skill first and then start easing in and embracing plots and things of that nature. So this is especially useful if you're working with embedded hardware. You don't really have that luxury, so you'll have to settle for things like serial output that just gives you a stream of numbers, and you'll just have to use those to see if something's working as you're expecting it to. And then, turning on the I gain is as simple as changing this value. And here's a PI controller. So it overshoots initially, and then it settles right back down. There's some oscillations up and down, but extremely close to 2. And you can actually implement a deadband to prevent these oscillations from occurring. And you can actually tune it, because I didn't really. I just took 2 values that seemed to work, 4 and 1. You can see how I can change this, and the code will rerun in your browser, so you can just briefly try some stuff out here. There's some harder or higher oscillations here. They're of a little longer period, as you can see, but this might or might not be good for your purposes. You can try this out, and yeah, that's the way you implement a PI controller. Obviously, you could just play around with this code and change this to your system dynamics, let's say, or maybe have it be an external function. That's all up to you. But yeah, with this, I guess that's all for now. Next time, I plan on going into a functional or data-oriented PI implementation, and take a look at some elements of object-oriented programming in Python that will pay off in the long run with much cleaner code that is easy to interface with different hardware specifications, and just has all sorts of boons all around. Now, some things that you can try at home is to try to add a D controller to the PI controller. I mean, you can look at that website that I mentioned. It's all down below in the description. And you'll be able to try some stuff out for your own, see how it works. Perhaps even try going ahead and plotting things, maybe implementing it on actual hardware. Who's to say? This is pretty, programming language agnostic. You can implement it in C if you want. But yeah, with that said, you can also try to add if statements, like I mentioned, to disable parts of your program, or maybe have some more interesting cutoff conditions where the controller disables itself when it's reached steady state, let's say. So these are all things that you could try and play around with. Just get some, get your hands dirty, play around with this, and you'll get familiar with what it feels like to code in control a lot better. So I hope you found this useful, and stay tuned for a next installment here. Thanks.